This video covers the two X-ray production processes that takes place in the anode, the Bremstrelung and the characteristic processes. The amount and energy distribution of the X-rays from the processes are different and influence the appearance of the final image. Also in this chapter, describes the two X-ray production processes and the challenges in the X-ray beam produced by changes in the KVP, MA, filtration, X-ray circuit, waveform, and anode material. Projectile electrons produced by thermionic emission in the cathode are accelerated by the high voltage to the anode, where either Bremstrelung or characteristic radiation is produced. The Bremstrelung process produces more than 90% of diagnostic X-rays. The remaining percentage are the characteristics X-ray. The kinetic energy of the projectile electrons is converted into heat and X-ray energy. Most of the projectile electron energy is converted into heat energy. Only about 1% is converted into electromagnetic energy of X-rays. The interaction that will occur depends on the electron kinetic energy and the electron binding energy of the electron shells. Bremstrelung is the German word for breaking or slowing radiation. Bremstrelung, also referred to as brems, is radiation that is produced when projectile electrons are slowed down in the anode. Bremstrelung interactions may only occur when the incident electron interacts with the force field of the nucleus. The incident electron with its negative charge is attracted to positively charged nucleus. The incident electron must have enough energy to penetrate the orbital shells of the atom. When the incident electron gets close to the nucleus, the powerful nuclear force field is much too great for the incident electron to penetrate. The force field makes the electron slow down or break and then causes the electron to change directions. As the electrons slow down, it will lose energy that is emitted as an X-ray photon. The Bremstrelung process produces X-rays of much different energy because the incident electrons are slowed down at different rates. Projectile or incident electrons that pass very close to the nucleus of the anode target atoms produce high energy X-rays than those that pass further away. These X-ray photons are called Bremstrelung photons, and their energy is the difference between the kinetic energy of the incident photon and the kinetic energy of the Brems photon. The amount of kinetic energy that is lost is dependent upon how close the incident electron gets to the nucleus. When the incident electron is farther away from the nucleus, very little energy will be lost, resulting in a low energy Brems photons. When the incident electron is closer to the nucleus, more energy is lost, resulting in a higher energy Brems photon. These incident electrons have the ability to interact with many target atoms to cause many Brems interactions. Each interaction will decrease the kinetic energy of the incident electron until the electron has no more kinetic energy and drifts away to join the current flow. The vast majority of diagnostic X-rays are produced by the Bremstrelung process. Characteristics interaction, on the other hand, occur in a tungsten anode when an orbital electron fills a vacancy in the shell of a tungsten atom. When a projectile or incident electron has sufficient energy to ionize or remove an orbital electron from an inner electron shell, a vacancy is created and atom becomes unstable. A higher energy outer shell electron will immediately fill the lower energy vacancy that creates a characteristic X-ray photon. The difference in energy between the binding energy of the vacant shell and the outer shell is the characteristic X-ray energy. The vacancy is usually filled by an electron in the next outer shell, but it is possible to have transitions to the vacancy from the shells further from the nucleus. This transition of electrons between shells creates a process called a characteristic cascade, which can produce many of X-ray photons for each electrons that leaves the atom. The characteristic interactions created at the anode target are called primary radiation. In diagnostic X-ray tubes with tungsten alloy anodes, the most common transition is from the L shell to the vacant K shell. Only K shell vacancies from high atomic number elements produce characteristic X-ray photons with high energy to be useful in diagnostic radiology. K characteristic X-ray photons produce a discrete spectrum, meaning that only X-rays with the characteristic energies are present. All characteristic X-rays resulting from L to K transitions in a tungsten anode have an energy of 57 kV. This is the predominant characteristic X-ray from tungsten. A less likely transition would be an M shell electron filling the K shell vacancy. M to K transition produce 67 kV characteristic X-rays. To produce K characteristic X-rays, the K shell orbital electron must be removed. If you enjoy watching this video, don't forget to click the like button, share to your friends, and subscribe to Earlyseven YouTube channel for more rad-clusive videos.